Going back to our earlier discussion regarding precision, the uncertainty entered in this field represents essentially the relative precision of the actual number entered into the value field. Note that when the choice is saved, the overall attractiveness of the choice is automatically calculated and displayed on the form. Now that we have entered and ranked our attribute weights and entered the data for each project, we actually have an initial project ranking for each project. While this is useful in some ways, remember that it only represents essentially a single model point, one set of attributes, an attribute weights, and a single value for each project attribute. Now, we're going to move on to the on steroids part. We're going to use something called a Monte Carlo simulation. I know that many of you are already very familiar with Monte Carlo simulations, but for those that aren't, Monte Carlo simulation methodology was named after Monte Carlo, Monaco, a city that is famous for its casinos and games of chance, such as roulette wheels, dice, cards, and slot machines. Games of chance exhibit random behavior within the context of the game equipment and rules. For example, a shuffle deck of cards will contain 52 cards, but the card order is random. Monte Carlo simulations involve creating multiple random outcomes, usually based on probability distributions, and then statistically analyzing the results. This type of Monte Carlo simulation is widely used in predictive financial modeling. One type of OPSI Monte Carlo simulation involves creating thousands of randomly generated decision models within a set of defined parameters. A portfolio of choices is then evaluated in each model and the results analyzed. Now, I know that sounds somewhat complicated, and it can be if you're trying to do it with spreadsheets or software that you have to do custom programming, but OPSI makes it really easy. The first thing that you have to do is to decide what kind of prioritization you want to run. With OPSI, you have three choices. First, you can choose to vary the attribute weight such that the weights change, but the rankings remain the same. In other words, the first ranked attribute will always be first, the second ranked attribute will always be second, and the third ranked attribute will always be third, but the weights between them will be different for each model. In this type of prioritization, the project attribute values are always the same. I've sometimes described this as being like having your portfolio analyzed by 10,000 people who agree on the same attribute ranking but not on the same weights, and then getting the average of all the results combined. And that's why I say that 10,000 heads can be better than one. Next, you can choose to vary the project attribute values within the uncertainty that you defined in the projects while holding the attribute weights constant. You can choose three different types of distributions for the project attribute weight distributions: a normal or Gaussian distribution, a uniform distribution, or a triangular distribution. Third, you can choose to vary both the attribute weights and the project attribute values simultaneously. This type of prioritization will combine the uncertainty of the model with the uncertainty of the data. Naturally, these types of models tend to show the largest uncertainty for each project, but they also tend to give the most robust and defensible project rankings. Next, we pick the number of simulations that we're going to run and the highest attribute weight allowed. In other words, the number one ranking attribute will never have a weight higher than that, and the others will always be below it. So, let's set it up and run it. So the first thing that we're going to do is to name our prioritization, and in this case we're going to call it combined since that's the type that we're going to use. We'll click the combined. We're going to use a uniform distribution for our choice distribution for the uncertainty. We're going to run 10,000 models, and the highest weight is going to be 6,000, so there'll be no weight that can be higher than that. Then we click prioritize and it runs. Now, once it's complete, we get to see what a project prioritization on steroids looks like. This table shows each project, the average rank obtained in the simulation, the single highest and single lowest ranks, the cumulative percentage ranks, which indicates the strength of the ranking, and then the average value and the standard deviation of that value. Now, that's a lot to see in just a table, so let's take a look at it as a chart. In the statistics chart, you can see the same thing, but it's much more compelling graphically. The average ranking for each project is represented by a point, and the standard deviation around that average is represented by the bars above and below. You can also modify this to see the maximum and minimum. And by double-clicking on the project on the chart, you can open and see the actual distribution of the value for each project. Remember this, because these are the distributions that are used when we do simultaneous portfolio optimization simulations. You can also scan through all of the distributions and open them up individually, as you can see here. This form contains the distribution thumbnails for each project, so you can scan through and get a sense of what the distribution is for each individual project. Some are skewed high and some are skewed low. You can also double-click to see the distribution in detail with the various statistics associated with it. But I want to go back to this chart because there is a tremendous amount of information condensed into each data point. Since each project had 6 weighted attributes and 10,000 simulations were run, each data point represents 60,000 individual calculations. The entire prioritization required more than 1.4 million calculations. Not bad for 2 minutes worth of work. Now, compare this with bubble charts, one of the more popular graphical representations of project portfolios. With bubble charts, you can see 3 dimensions of data, and it is usually difficult to see the third dimension because the bubbles begin to cover each other up. Most of the time, when vendors show bubble charts, they show them with 10 to 15 projects. The reason that they don't show more is because bubble charts become pretty useless as more and more projects become added to the portfolio. I could also discuss some of the graphical weaknesses of bubble charts in representing data, but that would be beyond the scope of what we have time for here. So now you can see why I call this project prioritization on steroids. If this were a typical project prioritization, you'd get a single data point result for each project based on 6 calculations, or 144 calculations in total. You wouldn't see any of the uncertainty around each project's value, including the distributions. Essentially, for the 24 projects, you'd have 24 single answers based on a single simple analysis. You'd know nothing about the uncertainty surrounding those points, and as we just saw, that uncertainty can be significant. But remember that the goal of project portfolio management is to select a set of projects that yields the maximum value from our constrained resources while not exceeding our tolerance for risk. This is where real optimization becomes critical. And it's not just something that can be done manually for any project portfolio of any substantial size. This project portfolio has only 24 projects in it, but there are 16.8 million possible subsets of projects to choose from. That number grows exponentially with each added project, so the odds of manually finding an optimal portfolio using a spreadsheet that meets multiple constraint criteria in even moderately sized portfolios is about as likely as winning the lottery. The question that I'm asked is, well, can't you just test each possible configuration? The answer is that you can for small portfolios, say around 20 projects with slightly over 1 million possible solutions, and OPSI has this capability. But for larger portfolios, it becomes very time-consuming, even with fast computers. And by time-consuming, I'm not talking about hours or days. I'm talking about years or even centuries. So, OPSI includes several custom optimizers that allow you to find optimal solutions quickly. Therefore, you can test different constraint combinations such as varying costs, risk requirements, resource requirements, and timing to come up with the best value-adding portfolio for your business. Now, let's see how this works. First, we're going to close the prioritization results table in the original portfolio. Now we can see the prioritization has been saved. So we switch over to the Decision Models and Portfolios form to open up a new portfolio that has been saved for us automatically. This is the portfolio we're going to optimize. So we open it up and click on the Optimizer button in the upper right-hand corner of the form to open the Optimizer form. You can see that the Optimizer is all menu-driven. The Optimizer itself will provide an initial set of suggested parameters based on the number of projects in your portfolio. You can also adjust the parameters as necessary. First thing that we're going to do is select the constraints that we want to use. We're going to constrain our cost to not greater than $300 million. We're going to constrain our resources to not more than 40 FTEs. And we're going to constrain our percent probability of market success to an average of not less than 65%. And we're going to constrain our percent probability of technical success to an average of not less than 65% as well. These last two constraints essentially fix the average risk for the entire portfolio. The OPSI optimizer is unique in that it lets you set average not less than and average not greater than constraints, and you can see how useful these are. Next, we'll name the optimization, and then we'll click the optimization button at the bottom to start the optimization. The optimizer progress form shows us how the optimization is progressing, and the lines in the chart show the relative current maximum, median, and minimum of the current data set, as well as the history of the optimization as it has progressed. The optimization is running in real time since it only takes about a minute to perform, but you can see how easy it is to set up and run. You can constrain up to 30 different parameters simultaneously. For example, if you had limited resources, such as project managers, developers, testers, graphic designers, and so forth, you could set up each one as a constraint and find the portfolio that maximized the value returned from that combined set of resources. During the optimization, it automatically runs the selected portfolio in a Monte Carlo simulation to create the distribution of outcomes that I showed you at the beginning of the webinar. After the optimization is complete, you can see the results in this form. So it found a set of projects with an overall portfolio value of 466, and it met our constraint criteria as follows. The cost of the portfolio is $297 million against our constraint of not more than $300 million. It uses 33.5 full-time employees against our constraint of not more than 40 full-time employees. The average probability of market success is 73.1 against our constraint of an average not less than 65%, and the average probability of technical success is 65.4% against our constraint of not less than an average of 65%. In the interest of time, I ran a number of other optimizations under different constraint settings. Each time an optimization is run, it is saved in this list form. By clicking through each optimization, you can see how it compares with a base optimization. A check mark indicates that the project was included in the optimization, and an X indicates that the project was excluded from the optimization. The no symbol indicates that the project was forced out prior to the optimization, or in other words, the analyst predetermined that they did not want the project included in the optimization. And the arrow symbol indicates that the project was forced in by the analyst prior to the optimization, or in other words, the analyst predetermined that they wanted the project to be included in the final result of the optimization regardless. We can also compare all the optimizations using the compare optimization form. Each time you perform an optimization, it is saved as a portfolio view. This allows you to compare different optimized project subsets much easier and faster than doing it manually. Notice that each time you select one, the results are displayed in the Efficient Frontier form for easy comparison. You can also create your own portfolio views and run simulations quite easily. So now, instead of arguing about which projects are in and which projects are out and about attributes and attribute weights, your portfolio selection teams can discuss what set of constraints they want to use to select their portfolio, knowing that each one of these points already represents an optimal portfolio from value-ranked projects. Simultaneous portfolio optimization simulation is just one of the new features in our latest release. So if you'd like to try OPSI for free on your desktop, just sign up by clicking on the I'd like to try OPSI button on this form. We offer free product support to all our demo users during the trial period, including a 1-hour initial training period. So, if you'd like to try this on your project portfolio, be sure to sign up today. Finally, I wanted to thank you for joining me today on this webinar. As you can tell, I'm really excited about this release because of the ease of use and the value it brings to our customers. One of our major focuses is to bring the power of great business analytics to everyday managers who aren't spreadsheet wizards and don't have time to become one. So if you're one of those who are ready and interested in moving to a much higher level of quantitative project prioritization and optimization for your business or for your consulting practice, I encourage you to sign up to try OPSI today.